Hi, let's look at the metals, nonmetals, and metalloids like we discussed last time. So we do have to have put it in a table. The metals are in the lower right corner, right? And the metalloids in between, right? And the nonmetals are in the upper left corner, right? So it's a good idea to memorize the ladder. So the ladder has in-between properties of metals and non-metals. So we don't have to really specifically memorize what's the metalloid's properties. The metalloid properties are in between the metals and non-metals, right? So in-betweens are easier to memorize. So you just memorize the two extremes, the metals and the non-metals. Okay, so we look at some other properties and trends in the periodic table that we should know. So if you look at the atom, this is the carbon atom, and the radius from nucleus to the first shell, that is atomic radius, simple r, and the atomic radius is normally you see in the patterns, right? The other property you can see or you can talk about is the diameter. That's the twice of the atomic radius, atomic diameter, right? So now these properties are going in the same direction. They have the similar quality, right? And therefore it's easier to think about the radius, the diameter, the volume is actually can be considered as atomic size. So it's an easy way to look at it. So the atomic size will indicate what is the radius, what is the diameter, right? We are not trying to memorize specific numbers, right? We need to know the trend. So it's a good idea to look at atomic size for both of these, the radius and the diameter size, right? Okay, so we can look at how it is changing in the periodic table, right? So in the periodic table, it would be changing in this fashion. So if you look at a simple box for the periodic table, so from left to the right, the nuclear charge, that's the first property we want to look at apart from the size. The size matters for it. So it will be increasing from left to the right or along the periods. It will be increasing the nuclear charge. Okay, so that's just how many protons in the nucleus, right? And if you look at in the group, in the families, it will be increasing from bottom to the top, right? So that's how the nuclear charge, but I have put here Z effective, or we call the effective nuclear charge. So that is basically the net effect from the nucleus towards the electrons in the valence shell. So why we care about the valence shell and the nuclear charge? Because that dictates the size of the atom and vice versa, and also that matters for the chemical reactions, right? Chemistry is all about the reactions. So the Z effective or the net effective charge is Z minus S. So that is basically proton minus shield electrons. So what's the shield electrons? We put it in the blue, light green color. This is the total electrons are Z, which is total number of protons equal to the total number of electrons, right? So that's all of them. In this case, it's 6 electrons, right? Now, what's the S? S is inside the shield, and those two are actually co-electrons. So in this case, we have 2 co-electrons for the S. So S is the shield. What's the shield means here? It is shielding the valence electrons attracting to the nucleus, right? So it diminishes the effect. So therefore S is a shield to the nucleus from the valence, right? So we're going to use this formula. If your class is talking about it, your prof is talking about it, we should know this formula, right? So you can just plug in this case Z is 6 and S is 2. 6 minus 2, it would be 4 effective nuclear charge, right? So that's the first property we should know. And let's move on to the next property. So the next property is, so let's correct this one. So the arrow should be like that. So from left to the right, from bottom to the top, that means the net effect will be going towards upward, both arrows, and then that would be fluorine. Fluorine will have the highest Z effective, right? Now, the next property we should be looking at, the periodic property for number 2 should be atomic radius, right? Like I said, so it's good idea to think about atomic size. That's why the smaller cage that I put there with a few sizes of atoms, right? And the atomic radius or atomic size. So let's finish the labeling here. Nuclear charge, that's based on the Z effective, so right? So that's number 1. So let's move on to the number 2, which is atomic radius, right? So like I said, I would like to generalize it as atomic size. That's why little sizes, the balls I put to represent atoms, right? So that because atomic radius is depending on the radius and diameter, which is simply the size, right? Look at the 2 boxes. So the 2 boxes, or the 2 periodic tables that I'm putting in 2 boxes, right? So they should be, the size will increase from right to the left, and it will increase actually from top to the bottom. So we need to change this arrow. And atomic radius measures size of the elements and atoms. Yes, so this arrow has to be downward. This arrow is okay. So increasing from right to the left, from top to the bottom. So that means the net force or the net atomic radius or atomic size would be going into the lower left corner, which is cesium. So the cesium is the good example. We don't consider francium because francium is not a naturally existing element. It's a man-made one. So we're going to talk about the cesium, right? Let's move to the next property that we have to talk about, the ionization energy. So that's really an important one. We're going to learn quite a bit of patterns of ionization energy, from first ionization energy to this, as long as you have so many ionization energies. And let's look at the pattern first. So normally we're talking about the first ionization energy, right? So to discuss this ionization energy trend, we need to know what's the ionization energy, right? So the ionization energy is, yeah, let's put number 3 here. Okay, so ionization energy is actually pulling out an electron from a gaseous atom and making a gaseous positive charge and removing an electron, right? So this depends on the size and the nuclear charge. So when you look at the size, smaller, it's going to be getting harder to remove an electron. Why? Because electrons are attracted to the nucleus, right? They're trying to keep it. So you need to have more energy to pull that out. So let's see the trend here. So it's increasing upward, and the fluorine has the highest ionization energies, right? Now, in any of these cases, we are not talking about the noble gases or inert gases. They are different completely, right? So the ionization energy, or IE1, is hydrogen gas and becoming hydrogen plus, and ionization energy 1 will give you some energy. That this is a endothermic, you have to provide the energy, it's a positive, right? You also can take carbon gas atom and remove one electron, makes the carbon gas plus, and that's ionization energy 1. From the gas, carbon gas plus, you can remove another electron, it'll give you carbon 2 plus gas, and that's IE2. And we can go on, ionization energy 1, ionization energy 2, ionization energy 3. As long as you have electrons, we can remove them and put a label as ionization energy 1, 2, 3, and so on, right? So we need to know all of these patterns, and so I will do a few more questions based on that once I get those questions, right? Now the next property, number 4, is electronegativity. This is also really important property. So the electronegativity, we are talking about the nature of covalent bonds. So I haven't talked about bonds yet. For now, we will look at hydrogen, H2, and HCl, right? Just for memorization, electronegativity changes from left to the right along the period, increases from top to the bottom along the groups increasing, right? So that's how it works. That means smaller the higher the electronegativity, right? So we can put the sum of the electronegativity increasing to the fluorine. Again, the fluorine has the smallest size, if you remember, and therefore it holds the electrons really tight. So fluorine has the highest electronegativity. So I kind of call it fluorine is the queen, right? Okay, now, so we can also compare or just simply look at it. Hydrogen molecule. Hydrogen molecule H2 has 2 hydrogen atoms, and there's 2 electrons shared in the middle of the 2 atoms. So that's how you make a hydrogen molecule, right? So we want to compare hydrogen molecule with something like HCl. So the hydrogen molecule, just simply draw 2 atoms and 2 electrons keep together, little stick, you put it in the middle, and they are 50-50 equally shared electron pair in a bond. So therefore we call there's no electronegativity, right, for 2 hydrogens. But if you put H and a Cl, the 2 electrons in the middle, the covalent bond, will not be equally shared. Why? The chlorine has plus 17 protons and hydrogen has plus 1. So therefore 2 poor negatives electrons are going to be pulled into the chlorine. That's called the delta minus. It's a smaller change of the electron cloud, right? So due to the electronegativity, this change leads to polarity. We will talk about polar molecules later. So the hydrogen H2 is nonpolar, HCl is polar, right? Okay, so there's another property we should talk about. That's the electron affinity. So when you say electron affinity, we are talking about 1 electron, and affinity means attraction to 1 electron. Who is attracting to 1 electron? An atom. So remember that way. This is important, the definition. So it's going in the same direction like the electronegativity, but the electron affinity definition is different, right? So it's similar to electronegativity, but not the same, right? So that means if we draw the box and have the pattern, it would look the same, right? But electron affinity is an attraction of a free electron to a neutral atom, to an atom. So that's the definition, right? So we don't use that much of electron affinity, but it's good to know, right? So that's all for today, and let's do a few questions next time. Thank you.